Okay, so this lesson we're going to talk about exercise 9L, differentiability. Yesterday we talked about the continuity of the function, and these two exercises are sort of like related together. So we're going to start from the last lesson by drawing an absolute value function. So let's just say if we've got an absolute value function look like this way here, all right? So like a very standard absolute value function. This is the y, that's x. Here's the absolute value function y equals to absolute value of x. Okay, now if you just look at this part of the curve here, if you look at this part of the curve, right, it's a straight line of 45 degrees, so the gradient of this line is equal to 1. And then on this side, the gradient of this line here is equal to -1. However, for example, if I want to look at this point, which is a sharp turning point, if you look at this one here, can we differentiate at this point? Are we able to differentiate it? The answer to that question is no. Okay, the function is not differentiable at that point. Okay, at x equal to 0. You can sort of differentiate this function here, alright, and then we know the derivative is equal to 1 once we know the equation of this function. We can also differentiate this function here, this part of the function. We can create a piecewise function, like this is x minus x, depends on what is x, okay? However, we can't differentiate this entire function when x is equal to 0. There is no value there. Okay, so how do we know if a function is differentiable or at a certain particular point? We need to know two conditions here. All right, so a function f(x) is called differentiable at x equal to a if it satisfies two conditions. All right, the first condition is the curve or the graph has to be continuous at that particular point. So for example, if the curve is like stopped at a point here, all right, it's not continuous. Obviously, you can't find a derivative at this point here. There's no point of finding it. The point is not even exist. And then if the point is like, a sharp turning point, you can't find a derivative at those points here as well. You can't say, oh, the tangent is just going to be horizontal. It doesn't work this way. Okay, so there are two conditions need to be satisfied. So therefore, we can actually differentiate. So a function f(x) is called differentiable at x equal to a. Okay, now when the first condition here is the graph of the curve is continuous. All right, at least it has to be continuous for the point that you want to differentiate. All right, you can have the curve that's not continuous, but you don't. You can still differentiate that curve, like y equals to 1 over x. But then this is actually quite important. It has to be continuous at x equals to a if you want to differentiate the function at x equal to a. Alright, so look at this function here, y equal to 1 over x. That is not a continuous function. It's on a hyperbola. So you can still differentiate the function, but that just means you can't, find the value of the gradient of tangent when x is equal to 0. It's undefined, and there's no point of finding it. Alright, and that's the reason. The second, oops, just lost my Apple Pencil. Right, so the second condition here is the graph passes through the point where x equal to a without a sharp corner. All right, there is no sharp turning points there. Okay. So the graph passes through the point where x equal to a without any sharp corner. I usually just say sharp turning point. Okay, and the resulting tangent is not vertical there. So we're going to talk about this one as well. All right, this is actually quite important. Sometimes you can have a sharp corner, or I would say sharp turning point. You still be able to differentiate at that point, which is sort of like it's a special case where you have a vertical tangent. Okay. Alright, so if the tangent is vertical, then its gradient and also this derivative is just undefined. Now, let's look at one of the example. I'll just try a few examples. It's a simple exercise, so it's not that hard. Okay, so I would like to just try the example from the textbook. Alright, so have a look at this piecewise function here. f(x) is equal to x squared minus 1. For x that's less than 1. And 2x minus 2 for x that's greater than or equals to 1. So the question here is, how do we know if the function is differentiable at x equals to 1, for example? Okay, so do we know if the function is continuous? Do we know the derivative is constant? All right, so for the function. So to sort of like doing this question here, you can actually draw the diagram if you want to. Usually the diagram really helps you to actually can see that, you know, if the function has a sharp turning point or not. So for example, the first part of things here is we have a parabola. So we've got a parabola going this way. Okay, oops, like that. And then this is one x is less than 1. So I'm going to put an open circle around here. All right, next we have a straight line, all right, which is 2x minus 2. So we've got a straight line passing through the same point, okay? So like a minus 2 is here. And 1 is here, so it's going to be going like this. So we've got a straight line, okay? It's kind of like, you know, a parabola again, but that's not really a parabola. It's a straight line on this side. Now, the question here is, how do we know if the function is differentiable at x equal to 1 or not? So the first thing you do is, after you sketch the graph, you know the function is continuous at this point. So that's pretty good, all right? Continuous is the first condition. At x equals to 1, that's good. We know the function is continuous. How do we know, or how do we check if function is continuous or not? So without a diagram, then in that case, all we have to do is substitute this value inside here and inside there to check if you get the same y coordinate or not, okay? Then you can prove the function is continuous at that particular point or not. Next, after we finish continuous, we need to know if the sharp turning point, or if there's any sharp turning point. Now, it's pretty hard to see if that's considered as a sharp turning point or sharp point or a smooth sort of curve here. What we can also do is we can find the derivative for both function, all right? And then we can check the gradient at that point to see if the gradient is consistent or not. All right, so the derivative of the first function is 2x. The derivative of the second function is 2. And that's for x is less than 1, and that's for x is greater than or equals to 1. So as you can see here, all right, if we substitute when x equals to 1 into here, the derivative is still equals to 2, which tells you the gradient is equal to 2, and that is consistent with the gradient here. So that tells you that, you know, we can have it, the function is smooth and differentiable, you know, at x equals to 1. So f dash, oops. Okay, so we can just write down f dash x or f dash 1 is equal to 2. Okay. All right, f dash 1 is equal to 2 for both functions here. So therefore, the function of the curve, all right, is differentiable, okay, at the point. Okay, when let's just call this point as P, at a point P, 1 and 0. Okay, so that's just one example to show you if the function is differentiable at that particular point or not. Okay, all right. So now let's move on to another example. This time I'm just going to find an example from the textbook. All right, I'm just going to pick a question from the textbook to see if that's differentiable or not. I'm just going to do it, you know, probably find a piecewise function as well. Okay. All right, that's a good question. Question 7 from the textbook, all right? So the question asks you to actually sketch the first part of the question. Sketch y equals to, it's a piecewise function, so you've got the first one, the square root of 1 minus x plus 1 squared, for negative 2 in between of x, and so for x between negative 2 and 0, and then it's equal to square root of 1 minus x minus 1 squared for x between 0 and 2. Okay, so that's just this, you know, describe what happened. All right, so sketch the function, and then the question asks you to describe, okay, the situation at x equals to 0. Okay, so how do we do this one here? I'm just going to do the first part, A. Part B is just same, you know, different question, but using the same method. You can try this by yourself. All right, first of all, all right, let's just break this function into 2. So first step is you need to realize what kind of function is this. Okay, you've got a square root. You've got 1 minus the terms inside. Sorry, I'm just going to rewrite it. 1 minus x plus 1 square. Now, if we square both sides, you should be able to see that y square equals to 1 minus x plus 1 square. And if you move this term to the left, you get x plus 1 square plus y square equals to 1. Hey, that's an equation of a circle. All right, with center equals to -1 and 0. That's the equation of a circle, all right? So once you know this, all right, and the radius is just equals to 1. So once you know this information, then you can sketch the function, and you know this is positive, all right, square root, which means, that's positive half of the semicircle, the upper half of the semicircle. All right, so let's first identify the center of the circle here, which is that one there. Okay, the radius is equal to 1, so therefore there's 1 here, there's 1 there, there's -2 here. So we have a semicircle shape. Okay, well, that's a pretty good semicircle. Freehand perfect semicircle, actually, I would say that. All right, next, then, well, let's have a look at what's going on with the domain. The domain of the function is between -2 and 0. Great, it's between -2 and 0. Perfect. All right, next, now we're going to deal with the second function here. It is a semicircle again. All right, so with this function, y equals to square root of 1 minus x minus 1 square. So that becomes another semicircle, but the only difference is this time the circle has a center +1 and 0. Radius is still the same, which is equal to 1. Okay? Based on the function here, so you can expand. You can square both sides and rearrange it. You should be able to get to this. All right, and then the question asks us to actually sketch from 0 to 2. All right, makes sense because now the center is 1, the radius is still equals to 2, so we'll have another semicircle this way. That's pretty terrible because my scale is not perfect. Okay. Okay, not as good as the first one, but anyway. All right. Now, the question asks us to actually describe what happened when x equals to 0. So, have a look at this point here. When x is equal to 0, okay, clearly it's not. Well, firstly, it's continuous, okay? So that the curve is like going this way, and there's a corner here. It's continuous, all right? That's something you need to understand. It is continuous, good. So we can just say, hey, at this point, at x equals to 0, all right, the curve is continuous. All right, so that's good. All right, it's continuous. All right, now, how do I know if it's differentiable or not? So at that point. Next, we need to see, hey, there's a sharp turning point here, so it looks like the curve is not differentiable at that point. Is there a way we can prove it when we substitute the value inside? I guess yes, we can prove it. So in order for us to prove this, we can find the derivative of the function. So we have f(x) is equal to y equals to the square root of 1 minus x plus 1 square, and y equals to 1 minus x minus 1 square. Okay, so if we want to find a derivative, the first thing we do is we change the square root. So instead of having a square root, we can have to the power of half, like this. All right, to the power of half as well. So therefore, f dash x is equal to y dash equals to half 1 minus x plus 1 square to the power of minus half times by the derivative of inside function here. Remember the chain rule, which is a bit annoying there because that's -2 x plus 1. Okay, all right. Okay, the next one is half 1 minus x minus 1 squared to the power of half, -half, times by, same thing, this time is negative, so is that -2? Why? Yes, -2 x minus 1, that's all. Okay. All right, now, of course, you can actually simplify the half and 2, half and 2. Right, but that's not really important. What's important is I want to substitute 0 inside here. All right, to see if the derivative is the same. All right, so I'm going to just do it here on the same page. if we substitute 0 inside the first one, think about it, all right? If we substitute 0 here, that's 0. So you've got 1. 1 squared is 1. That gives us 1 minus 1 is equal to 0. So this entire part disappeared, which is equal to 0. Times by 0 plus 1, which is 1. Now, second one, if we substitute 0 inside, same thing happens here again. That becomes 0. However, this one is... wait a minute, did I make a mistake? I think I made a mistake. 1 times by 0 is not 1. It's actually equals to 0, yes. Alright, I can't believe I actually made a mistake here. Alright, is equal to 0. Let's have a look. Alright, so it's equal to 0. Then you can substitute the same thing here to see what's going on. If we substitute the same thing, I'm just thinking about what's going on here. Okay, let's have a look. Now, if we substitute 0 inside there, did I make a mistake? I think I made a mistake somewhere. Okay, probably I need to just start off a fresh page. All right, we do one more time. If I substitute zeros here, okay, 0 here. All right, that becomes 1. 1 squared is 1. 1 minus 1 is equal to 0. So 0 to the power of negative half is actually equals to 0. So that's good. All right. Okay, so that's 0 times by 1, which is equal to 0. Yep, so first one is equal to 0. The second one is if you substitute 0 inside, so you get negative 1 squared, which is 1. 1 minus 1 is equal to 0, and that's negative 1. So that's 0 as well. So it looks like it's differentiable at that point. That's not the result I'm looking at because the derivative at both points here is actually equals to 0. So that's not what I'm actually expecting to see, which is pretty interesting. Why this function is differentiable at that point. All right, you know what, I'm just going to check the answer. Just give me 1 second to see what's going on here. I don't think this is differentiable. It looks like, you've got a sharp turning point, but just bear with me. I'll just check the answer. Yeah, okay, so, all right, yep, okay, so good, that question, yes, it's not. Okay, so yes, the function is continuous, all right, and yes, we have the derivative both equals to 0 at this point here. The reason I made a mistake. Okay, yeah, how mistake I'm making here is if I do a proper substitution, you end up with like 0 to the power of negative half times by 1, and then 0 to the power of negative half is undefined. Okay, same thing applies to here. So it's undefined, which then leads to the next, the next concept I'd like to talk about. There is a cusp, so which is like CUSP, cusp, at this point, which tells you that we have a vertical tangent at this point. Yep, that makes much better. Okay, so yeah, I was thinking about it shouldn't be differentiable at that point. So, oh, that's a bit too thick. All right, that's better. So we've got a vertical tangent. Okay, so it's actually called a cusp at this point, where we'll have a vertical tangent at a point here. All right, oops. All right, yep, sorry it took me that long to realize it's defined, because I didn't realize there's a power of negative half here. 0 to the power of negative half is actually undefined because you are getting reciprocal of 0, which is undefined already, and then you square root it, don't even think about it, it's undefined. Okay, all right, good example. Yeah, I didn't expect to use that example to talk about the cups. I would like to sort of talk about the cups using a different examples. But anyway, all right, since we actually talk about it, all right, let's just try another example 3. Okay, so let's actually look at this function. All right, fx is equal to x to the power of 2 on 3. If we differentiate this function, we end up with 2 over 3 x to the power of minus 1 on 3 here. Okay, so same thing applies, all right? This function is continuous at the origin, and then f dash 0 is undefined, very similar to what we did before, because if you look at this, that's 1 over 0 and to the cube root of 1 over 0, which is undefined. All right, so if it's undefined, that means the function is never, it's sort of like it becomes infinitively steep on both sides of the origin, okay? If you substitute, think about this, if you substitute a really small number into x, like when x is equal to 0.00001 inside, you will end up with like the reciprocal of 0.0000001 is going to be a really large number, all right? Like 10 millions or 1 millions, all right? And then you do the cube root of that, it's going to eventually be a large number. So the gradient is going to be extremely large. Therefore, when you actually sketch the curve here, you end up with, at this point, you have a vertical tangent like this, vertical tangent, all right? Which means the curve is increasing on this side. How do I know the curve is increasing? We didn't really talk about this before, but I can show you. When x is greater, so we've got a f dash x, right? It's equal to 2 over 3 x to the power of negative 1/3. So we can break that into two parts. If x is greater than 0, okay, think about it. If x is greater than 0, then f dash x is positive. So that means you have a positive gradient. So the curve is actually increasing. If x less than 0, then f dash x is negative. Okay, so therefore the curve is actually decreasing, so it goes like this. Okay, the curve is decreasing. And that's the reason. Now, some student will probably ask, well, the curve is increasing, but why is it not increasing like that? Well, if it's increasing like that, you're not going to have a cusp here. And also, if you study later for the second derivatives and we talk about the concavities, you will understand why the curve is concave downwards when it's increasing. Okay. All right, so therefore, as a little summary here, so the point 0, 0, or the origin now, is actually called a cusp. All right, that's all you need to know, all right, for this exercise. I feel like those 3 examples is enough for you to actually understand how the function is differentiable at a particular point, and what is the requirement to be satisfied before you can make a conclusion saying that the function is differentiable. And if the function is not differentiable at that particular point, do we have a vertical tangent? Okay. Thanks for watching.